We call this series of programs the secret of flight. And we could have probably called it also the mystery story of the streamline to be up to date. And you might wonder, what's all this secret about? Can't you buy yourself an airliner ticket, drive out to the airport, board the plane, take your seat, fasten your seatbelt, and with roaring engines, off you go. After the plane has climbed to the proper altitude, there comes the voice of the captain through the loudspeakers telling you that you are flying at 20,000 feet altitude with 320 miles per hour, and that the weather is fair ahead and you will have a pleasant flight. So you make yourself comfortable in your seat, read your favorite magazine, light a cigarette, and probably look out through the window to the wide plains, to the little farms and towns. And you might also have a glimpse through your window of the wing and a few of the engines against some beautiful cloud formations which you see at the far horizon. Well, there is certainly no secret anymore that this slender wing and these four powerful engines support an aircraft of more than 100,000 pounds, which connect towns, countries, and even continents with the fastest means of transportation. What was once a dream of the pioneers of aviation 50 years ago became a reality through a scientific and technical development of unforeseen rapidity. But while you are looking out there, something is still mysterious to you. Where is the road on which you travel? Where is this element which supports your flight with such invisible power? Well, you feel the forces of the air on the aircraft, and the pilot can tell you how these forces react if he changes his controls. And you probably could even ask a scientist, an aerodynamicist, and he will give you long mathematical explanations of the laws of fluid motion and how you can figure out these forces, at least approximately. Well, this would not satisfy your search for better understanding. If you only could see what happens, if you could make this process visible, you would at once conceive basically what's going on. And it was one of my pet projects to make an instrument where we could visualize basic flow processes. You know, a picture is better than 10,000 words. And if we can make nature to show this flow process visually, then we would have a mean of simple conception, and we would not need all this complicated mathematical explanation. And therefore I built this smoke tunnel. And there it is, the view field of our test section. Now the white lines which you see there are really streamlined. You might think that we have put some threads, white threads in there, but this is not so. I can prove it to you when I shut the tunnel off and the motion slows down, then at once you see that this is really a smoke pattern. And it really gets a beautiful pattern as you see it now. If I start it again, there are our straight streamlines. Now, if we have something in the tunnel, some model, we would see the flow pattern which is formed around the model. Watch this. There it is. The streamlines now don't, as you see, bounce just against the plate. Oh no, they go smoothly over it, but at the corner of the plate, they stall away and don't come back to their original position in this tunnel. Oh no, there is behind this plate a large area of dead air. And when you would think you would stand there, you might feel only the local turbulence and a little flow from the backside. But it is especially interesting to see this transition while this plate flips up. And therefore we have made a slow motion picture of this action. First we see the normal view field as you saw it out there. And now the plate comes up. And watch this. It forms first a small circular vortex behind the plate which floats away. And then the whole large area of dead air in the lee side of the plate begins to form. You actually see a little oscillation on the plate itself because it's sprung up by a spring which makes some damped oscillations until it gets into this steady position. You see on the border of the dead air and the flow itself, you see what we call a discontinuity line, where a mixture happens between the outer air and the flow in the lee zone of the obstacle. You know, to see what's really on such a flow picture, you have to get acquainted with it, and it might be quite new to you. Therefore, we want to show you this flip-up plate once more in normal speed as it is here. Now watch it again. There we go. There you see again this nice pattern of flow lines which go over this obstacle. And observe the reverse flow which you have behind the plate. It's really something which you might often experience in nature itself, where the wind suddenly comes from the other side due to such a reverse flow in a dead air zone. Now we want to go again and show it in slow motion. So straight parallel flow line, and pretty soon you will see here how this plate comes up and how this circular vortex is formed first and then floats away, and the large dead air zone behind this obstruction is formed. In the boundary between the lee dead air and the outer flow, you have small vortices, which you can see here, which always protrude into the dead air zone and form also such a wavy front between the flow, outer flow, and the calm zone behind the obstruction. On the other hand, one thing is interesting here, that the flow lines of the undisturbed flow go much higher than the height of the obstruction is. So if you stand behind such a thing, you easily can look over it without having any blow in your face. That is the secret of a windshield. While we are preparing the tunnel for another test, let me just briefly explain to you how this instrument works. Now, you might first ask, what is a wind tunnel? Well, a wind tunnel is an instrument to measure the forces of air on models' airplane parts. And we might even look into the Webster to find the right definition of a wind tunnel. Let me just read it to you. I think it's there. There it is. A wind tunnel. A tunnel-like passage through which air is blown at a known velocity to determine the action of wind pressure on structures, airplanes, etc., that are often in the form of models of reduced dimensions. Well, Webster certainly knows it. Now, this wind tunnel is a special one. And you can see here the top view of this whole installation. It consists mainly of three major sections: the intake section, the test section, and the blower section. At the intake section, we have a large nozzle and go into a silencer chamber where we have fine mesh wire screens in it to break up the large disturbances which might come from the outer, and also to damp out any noises which would come from the outer and disturb our flow. After we have made with these fine screens out of the air which comes in a micro-turbulent air, broken up in all little fine bubbles, we contract it through a nozzle, and due to this contraction, we get all the turbulence out and get a complete, smooth, steady flow into the test field. Then we blow the air from the test field into the blower section where we have a little settling chamber, take it out with the blower and through a smokestack, blow it out into our system. We control the models from a control panel, and our smoke is introduced at the nozzle where we have a smoke strut, a streamline-shaped strut where very fine tubes come out, and through each tube we blow the smoke into this accelerated flow. You might be interested to see such a smoke generator, which we have here put up for you so that I can demonstrate it to you. This instrument actually was designed by British scientists, and it works in this way. We have here an oil container, and through a communicating system, the oil goes into this tube where we have a heating wire on it, heat it up, evaporate the oil, which then goes into this chamber through a very fine nozzle. This jet stream of this oil vapor which comes out there is then cooled down by air, fresh air, which is blown through a pressure system into it. Due to that sudden cooling and expansion, the oil vapor forms a fine mist, which comes then out here as this smoke, a very fine smoke which does not clog up your lines. Now let's have a look around the tunnel. Here you look into the intake, the large nozzle which goes into the silencer chamber. The structure itself is mainly a wooden structure. Here we have the silencer chamber where we have the screens in. They are put in here and can be exchanged so that we can clean them, because to have clean screens is very important, otherwise our flow would be disturbed. From there, the flow, as I told you, goes into this nozzle, which is large convergent nozzle of a convergence of 1 to 20. In front here we have the control panel. Now, these three wheels are the model controls, where we can turn with them the models to give them certain motions of the angle itself, of flaps, and things like this. This is a mechanical connection through the back of the tunnel to three concentric tubes where you attach the model in it at the rear glass wall. Here we have the usual switches, the main power, and here are the lights. And from here you control the blower, the speed of the tunnel, and the blower himself. And with this little instrument we can measure how much speed we have through the test section. This tunnel we have built at the Collins Aeronautical Research Laboratory with the help of the Office of Naval Research in Washington. Now we get here to the test section, and let me show how we put a model into it. We open up the front window, supported because it's quite heavy. And here we have the model. You see, that is a kind of a bayonet attachment where we put it in, so, and then close the tunnel again. And through these controls, I can now move the model from here up and down. And now let's turn the smoke on. There we have it. And there is our flow field with the plate parallel to the direction of the flow. So you see practically no disturbance except this small turbulent layer, which is caused by the friction of the air on the surface of the plate. But now watch. When I turn the plate across the flow, first of all, it begins to stall, to break away a little bit. And then, when I turn it on more and more, and finally have it at 90 degrees towards the direction of the stream, we get that violent oscillating motion, a so-called Kármán street. Since Professor Theodor von Kármán was the first who investigated this phenomenon. You might see it even better if I turn the blower down so that the whole field slows down and we see it in a slower motion. See how these vortices are generated from the tips of the plate, always intermittent. See, now the view field fills up with smoke. And when we start again, then we have the transient picture of this flow, which we actually can observe much better if we have a slow motion picture. First, we see a straight wake with dead air extending from the plate backwards. Both sides are the same, but we see at once beginning an oscillation back there at the end of this wake, like on a flag. And this is transmitted slowly against the flow direction towards the plate. And finally, this results in an pulsating intermittent formation of big vortices from the corners of the plate. This we call a Kármán street. Since the well-known aerodynamicist, Professor Kármán, investigated this for the first time and found that only such an intermittent motion and position of these vortices could exist due to stability conditions. We will come to this later in one of our other programs. Observe here mainly the magnificent pattern of the flow and the speed which you have locally in these vortices, which is quite high, because you must think that this low speed picture makes about a second to a minute. You might think that this generation of these intermittent vortices is mainly caused by the sharp corners on the flat plate. But unfortunately, that is not so. Even a circular cylinder, a rod, would cause such oscillation. And we have put one cylinder into the tunnel, and when we turn the smoke on, then we see that we have the same type of a vortex street behind the circular cylinder. So actually, we have to have another form of body to diminish this disturbance behind such a body. Now my assistants have put in a streamlined body in the wind tunnel, and to explain the shape, the evolution of the shape to you, we have probably to go back to this phenomenon of the vortex street behind the body. Actually, you can observe this quite often in your normal life. For instance, when the wind blows against a wire, this fluctuation excites the wire and makes it to vibrate. So that's what you hear. This wire whistling is nothing than such a, as we call it, Kármán street behind the wire. Or you want to move an oar through the water or a round rod, and you will find that you can't move it straight. It always oscillates due to these vortices which you generate with the oar or with the rod. Now, this is certainly a phenomenon which we don't want to have in airplane design, because it would cause large oscillations and also lots of drag. To get rid of it, what you would do, first of all, you must see that the front part, on the front part of the body, the flow was nice and smooth, and your trouble started at the rear. Therefore, you have to do something at the rear, not make the front pointed. Oh no, let it be rounded. But fill out this rear part with a body which is slightly convergent, so that this vortex generation can never start. Here you see a typical streamline shape. And you see no vortex generation anymore. A small disturbance back there, this little blurred part where the air gets turbulent because we have friction on the walls of the body, which necessarily retards the airflow and makes small disturbances which cause here our smoke lines to blur out. Now, if we turn the body, we can also see it when we have not just a straight flow against it, but the flow comes now under a certain oblique angle. You see that then the disturbance gets somewhat larger. All these things I will explain to you in many of the later lectures, and I wanted to show you today mainly that such a device where we can make the flow visual, where we can see what happens, is a very helpful tool in our aerodynamic research, as we say it, or when you just want to make such flow phenomena understanding to other people. In our last program, we have seen several flow pictures in the smoke tunnel, and I have explained to you how this tunnel works. Today, I want to show you how we can determine the forces which act on a model in a tunnel and the different velocities which are there. Well, the forces which are produced by a flow over a body apparently are forces of the air pressure against such a body. For instance, when an aircraft flies, the lift is produced by pressure forces on the surface of the wing, and this keeps the airplane flying. Have you ever seen an airplane take off? Well, to show you this time when the lift begins to go, we have made a picture of a light plane taking off from a runway of an airport. And there it is. Let's look at it. First, we see the plane rolling on the ground, then it gains speed, and then the pressure forces are so large that they lift the plane from the ground and it flies, supported by the air pressures in the same way as, for instance, a weight would be supported, which is here laying on the table, by the pressure from the material of the table to the weight. It's exactly the same thing. Now, how can we do and see it in this smoke tunnel? We see there only a section of the flow. We see only a cross section. And to explain it to you more specifically, I have here a model of a light plane as we just saw him in our movie picture. And when I now take the swing off and show you the side view of it, then you might be able to compare it with what we have here as a model in the wind tunnel. There we have part of the wing, and we have outlined the fuselage with a thin piece of plexiglass on the rear wall of the tunnel. If I now turn the flow on, and we have our smoke generator going, then we can see the flow over this model, especially over its wing. first, as it took off, it was flat. And then the pilot turned it over and we got more lift and it lifted from the ground. Now, apparently, we cannot see any pressures. So we can only see the scales, for instance, on a pressure measuring instrument. And in flow, where we have quite low pressure differentials, we use what we call a manometer, a fine pressure gauge, which works in this way. We have a U-tube, and this U-tube is filled with colored water to a certain level. If we now blow into one tube, for instance, through this rubber hose, like this, then you see that the pressure which I exerted here through this hose on the water level is to be read by the difference between these two water levels. Here, for instance, let's see, 2.5 inches of water. Now, what is 2.5 inches of water? Well, we have a wonderful, simple English system of units. And then when we figure this all out, which takes us quite a while, then we find out that 1 inch of water equals 5.2 pounds per square foot. Now, what is pounds per square foot? You probably are not familiar with this type of unit. You usually measure pressures in PSI, as you measure, that means in pounds per square inch, as you measure it, for instance, on the tires of your automobile, where you have about 28 PSI into it. And you measure the same PSIs on a pressure tank, which you probably have in your basement for anything. So what is a PSI when we think of inches of water? Then we find out that 1 PSI equals 27.7 inches of water. So that means when we have here 1 inch of water, or sometimes even less in such pressures which we measure in a flow, then this is extremely small. Let me show how we, for instance, can measure how much flow we have in this blow of a vacuum cleaner. If I put, for instance, this hose direct against it, you see then that this blast gives us about, not quite an inch of water. And with some tricky formulas, we can figure out how much velocity this is. I don't want to annoy you with this. But you must think that these small pressures don't amount to anything when we think of the pressure which we have, for instance, in automobile tires, where we have compression of the air. So if we have a few inches of water, there is practically no compression or expansion of the air. And therefore, the scientist treats such flow as we have it in normal wind tunnels, or as we have it up to 300 miles per hour flight speed, as the flow of an incompressible fluid. Now I want to explain to you the correlation between the velocity and the pressure on a surface where we blow the flow over it. There's one important thing to understand. That is that when the velocity at a certain point of our model is larger than the average velocity, the pressure on the surface of this body is lower than the average pressure. And if the velocity is smaller than the average velocity, our pressure is higher than the average pressure in the whole fluid. That means we have to know all the time that if velocity increases, pressure decreases. And if velocity decreases, pressure increases. Very important to know. And to show you this and explain it as good as we can do it in this tunnel, we have put here a so-called multi-manometer. That means a multi-pressure gauge on a certain model in our smoke tunnel. Now let's have light so you can see the model. And if I now blow through the tunnel, then you see that this manometer reads certain pressures along the surface of this body. How we did it? Now, we have fine holes on the surface of the body. These fine holes are connected through rubber hoses, through the model here and out there, back there, on the tubes of this multi-manometer. And the other ones are all connected with the average pressure, which we read in front of this test field where our flow goes in with its mean velocity. We see now, since this is convergent, the velocity must increase. And since the velocity increases, our pressure must decrease. That means we must have kind of suction on the surface. The air must suck away some fluid out of this line. And this makes the water column go up here. So if the water column goes up, we have suction. And where we have the highest velocity, we must have the highest suction or the lowest pressure. That would be on such point like here. Now let's see. This point corresponds to this line. And you see at once this is the highest water column which we read here, where we have the highest velocity through this cross-section. Now if we turn the smoke on and let our smoke generator go, then we can see this flow field. And we see that when the velocity increases, our distance between the flow lines gets smaller and smaller. So if flow lines are very narrow together, we have a high velocity and we have a low pressure. How can we see this velocity business? Now we make a trick, and that is we pulsate the flow. That means we let pulses into the smoke system, and so our smoke comes out in fronts, little puffs. But we can even see it better if we observe it through an optical system. That means we take our high-speed movie camera and make a slow-motion picture of this pulsating flow process. And then we see at once that our velocity in this region is much higher than here. Let's just look at this film. There we are. You see a very interesting thing here, that the velocity increases first in the center of the smoke front and then goes with even velocity through the narrowest part of this channel. We call such a line which goes through there a timeline, because actually this indicates the particles of the air which come all at the same time into the flow and travel through there, and the different shape of this line shows us the time history of the flow. Now, to see another pressure distribution, as we call it, that means the distribution of the pressure over the surface. We have taken out of the tunnel one side of this nozzle, and then we have the flow over a hillside or over a hump, and we can see then how the pressure records now. There we are. I turned the flow on, and you see when we take this out and we have more space, our velocity doesn't go as high as it went when we went through this narrow nozzle. Therefore, the pressure doesn't read as high as it did read before. And we see one other thing. We see that the highest point is now this one. That means here. It reads here the highest velocity. And the velocity here, as it was before the highest, is now smaller and declines since the whole flow begins to slow down to the original cross-section which we have at the rear of the tunnel. Now, if we turn the smoke on, then we can see the flow field itself. Here it is. And we see at once that in this region we have the highest velocity, because there our flow lines are the most pushed together. Here down there we have even a little bit pressure. We see that because this one records a little lower than the average pressure. Now, if we do the same thing again with pulsating smoke, then we can see also the velocity field. You see, when we have normal velocity, that goes too fast. So I have to cut the speed out and slow the tunnel down, and then we can see it by eye. But again, better we see it in a slow motion picture, which we have here. There it is. There we see that the velocity at the lower part of the tunnel decreases considerably before it hits the bump, and then is suddenly accelerated. But the whole front bends over. Now, we have another little trick, because we want to demonstrate to you the flow and the pressure distribution due to this flow over a wing section or type of a wing section. Now we had this hump. When you think, the upper surface of this hump had almost the same shape as the upper surface of a wing, slightly rounded. So we take our hump and lift it up into the center of the view field. And then we have a large wing section-like model in the tunnel. And we can see now the pressure recordings on the upper surface of this wing section. When I turn the blower on, then you see here in this multi-manometer or pressure gauge, you see that we have again suction, lower pressure on the upper surface due to the higher velocity which we have up here. Interesting to see, first of all, the first one, which is this one, records a little lower than the average. That means here we have actually some pressure on the surface. From there on, the speed increases and the pressure goes down, and we have suction, and this suction on the surface sucks our water lines up, and this shows the pressure distribution over this surface of a wing section. If we now have smoke lines, then we can see the flow picture. And you see very clear that the velocity here is much higher than there. See how narrow the lines are here and how wide they are in this range. On the other hand, you see that here the flow somewhere goes to a point on the surface. And this we call the stagnation point, where the airflow stagnates. It is stopped completely and would record, if we would have here a pressure, the stagnation pressure, which is a higher pressure than the average pressure of the flow. Now, if we take again our method of pulsating the smoke, then we can see this velocity distribution. And to make it visible to you in this flow field, I stop the blower so that the tunnel slows down and we see a little bit at least these smoke fronts going over the wing section. Better we see it in a slow motion picture, which we have here. And there we see very clearly that the velocity on the upper surface of the wing section is higher than below, because we have a very distinct shift of the two parts of the smoke front which goes over the wing section. This shift of the timeline of the smoke front indicates lift on the wing section. And by some tricky mathematical calculation, I didn't want to explain to you here because you would sleep with it, you can calculate the lift you have on such a section from the shift which you see here. Now, you have seen this phase shift of the big wing section in our tunnel. And some of you might say, all right, that's due to the fact that this thing is so large and the tunnel is quite small. And therefore we have blocked some area above and the velocity must be higher. And you have cheated me. And I will tell you, I did not cheat you at all. And I can prove it. Because we put now a small model in this tunnel, like this here. And when we do the same thing, we pulsate the smoke again, you will see that again the upper flow is much faster, and behind the wing section, still far away behind it, you can see very clearly that you have this phase shift in the timelines. Now let's first look at this thing with the normal smoke on. There is the flow, and now we get the smoke generator going, and there's our flow picture. You see, this is an angle of attack almost zero. We measure it from the lower surface. And what you see here also, very interesting, is a little stagnation point. This is a stagnation point of this section in this angle of attack range. And if we pulsate the smoke now, then you see this velocity field. Well, you can't see much here. But if we look at the high-speed movie or the slow motion picture or at the smoke lines here, then we might detect this shift. Let's look at this here. There we have the same condition as we have put it here in the slow motion picture. And you see again very clearly this shift in the timelines, the same way as we saw it on the big wing section. Now, if we see this with a higher angle of attack, then the lift is larger, and therefore our shift in the timelines must also be larger. Now let's go back to our smoke lines in the smoke tunnel. We can see other things too, especially if I change the angle of attack. See, when I change the angle of attack, then you see that the lines on down here get wider and wider. We get more pressure underneath, and the lines up here get narrower together, so we have more speed, especially in this region. We increase the lift. Another thing we see is that behind the section, we get a larger area of turbulence, of air which doesn't have anymore the main velocity of the flow because it's blocked off and also slowed down by the flow on the surface. If we go much higher, then this blocking is so strong that the whole thing stalls away, as you see it here. And then we have no lift. It's a very difficult condition and very dangerous for somebody who wants to fly with an airplane. He has to learn that if you have too much angle of attack, your flow stalls, as we say it, and breaks away from the upper surface where you have most lift, and your airplane falls down and you have severe accidents if you stall an aircraft. Now I think we have understood how we can analyze such a flow picture, and we got a little idea why an airplane flies. In our next program, we want to give you a little story of the past. You see, this flow and basic law of fluid motion was well known for quite a while before any activity were on to try to solve the problem of the flying machine. And the first, I think, whoever at least made a model of a flying machine was a Frenchman named Alphonse Pénaud. He made a small model of an airplane with a propeller on it and had a rubber motor on it and flew it in 1870 before some of the members of the Academy of Science of France. In the Smithsonian Institute in Washington, there is a replica of this model, and I have here another one, which I can fly. Unfortunately, this area which we have here is a little bit too small to do this. And so we made a little film in the outside where I can show you how this Pénaud model, which is originated in 1870, that means it is now 76 years old, how it flies. From there, we will go through the up and downs of the first development of the flying machine, and we will see how the invention finally was achieved by the brothers Wright of this country.